Welcome to the second video in which we are quickly going to discuss fluid particle methods. As the name suggests, particle methods are based on the concept that individual particles are resolved in the simulation. And the liquid dynamics now follow the behavior of those particles. The advantages of those particles are that you are able to investigate non-continuum phenomena, for example, rarefied gases, and that it is quite easy to simulate free surface or two-phase flows, which is otherwise a little bit more complicated. And there are two approaches I would like to present you today. The first one is the molecular dynamics approach, and the second one is a smooth particle hydrodynamics approach. So let's start with molecular dynamics simulations. I prepared a video for you, which we're going to watch right now. Here you can see a mixture of oil and water, with the small molecules being the water and the big ones are the pentane. And as you can see, the molecules interact and the oil is forming a droplet inside the water. And as you can see in this video, the individual atoms are resolved and they interact with each other. And the overall behavior follows the individual particle dynamics. And this video should illustrate quite nicely these principles. So please keep in mind that if you use molecular dynamics simulations, you model and simulate the movement of individual molecules or atoms. This is pretty similar to the statistical physics approach we discussed last week. And the interaction between those individual entities is usually described by force laws. There exist various applications, for example, in the field of material sciences or in biophysics and biochemistry. And here, especially the interaction of proteins or DNA with other macromolecules is studied using this kind of approach. The second particle-based method is the smooth particle hydrodynamic simulation approach. Here, the particles do not represent individual atoms or molecules, but rather an assembly of fluidic particles. So we are talking about a different length scale we are going to simulate. This is very important to keep in mind. So this approach here is no molecular dynamics approach. It's more a computational fluid dynamic approach, but it also is based on the individual particle motion. And the motion of those individual particles is still described by the Navier-Stokes equation. And each particle is now influenced by a set of neighboring particles. This is a mesh-free method, and this is illustrated on the right-hand side. On the right-hand side, you can see blue particles. So those blue dots represent the fluid particles. And this image is illustrating how the central particle for which the Navier-Stokes equation is evaluated right now is influenced by a set of neighboring particles. All particles that fall within this circle have an influence on that particle. And this function in the middle is a weight function, which defines that closer particles have a larger influence compared to particles which are further away. And as in this method, the fluid is represented by those individual particles. It does not require a mesh, which has led to several applications, such as the simulation of free surface flows or two-phase flows. An example would be the simulation of an avalanche. And this method or this approach has also gained some interest in the field of solid mechanics, for example, for crack simulations. And the last application for this SPH method is the animation of fluids in movies. And for that, usually not the Navier-Stokes equation is solved, but a simpler equation which has nothing to do with physics. But the result, if you use this SPH method, still looks like a fluid.